Good afternoon to all. So last class we have seen electromagnetic relays. Today let us discuss about induction relays. So the induction type relays, we can even call them as magnitude relays. These relays work on the principle of induction motor or energy meter. So what is the principle of induction motor? So the induction motor is the one which works on the principle of electromagnetic induction. Okay, so what is electromagnetic induction? Electromagnetic induction is the phenomena in which the electromotive force induces across the electrical conductor when it is placed in a rotating magnetic field. You people already know the working principle of the induction motor. Just I'm briefly just revising it, that's all. So induction motor works on the principle of electromagnetic induction, and electromagnetic induction is the phenomena in which the electromotive force induces across the electrical conductor when it is placed in a rotating magnetic field. So you can even call this induction motor as the rotating transformer. I hope you know that. Okay. So this induction relay, we can even call it as magnitude relay, and it works on the principle of induction motor or an energy meter. Okay, so in these relays, a metallic disc will be there. Okay, a metallic disc will be there, which is allowed to rotate between two electromagnets. Okay, in these relays, okay, there will be a metallic disc. You can see here a disc here. Okay, there will be a metallic disc which is allowed to rotate in between two electromagnets. Okay, so electromagnets means some ferromagnetic material is taken, and to that ferromagnetic material conductive coils are wounded, and current is allowed to flow through those coils. When current flows through those coils, these ferromagnetic materials will be magnetized. Okay, so the coils of these electromagnets are energized with the help of alternating current here. Okay, so the when disk is placed in between two electromagnets, and when current is allowed to flow through the coils of these electromagnets, okay, what will happen is torque is produced in this disk, okay, due to the interaction of the fluxes. Okay, interaction of you can see two electromagnets are there. Okay, and because of the current flow in this and the coil which is wounded around this electromagnet, of course you can't see the coil here, but let us imagine a coil is wounded around this, and a coil is wounded around this also. Okay, and when current flows through the ferromagnetic material, what will happen? They gets magnetized, so the flux is induced. Let us assume in this electromagnetic flux induced is phi1, in this electromagnetic flux induced is phi2. Okay, so due to the interaction of one alternating flux with the eddy currents induced in this disk, or we can even call it as a rotor, by another alternating flux, okay, what will happen is torque is produced. Okay, so torque is produced within this disk, or we can call it as a rotor, due to the interaction of one flux with the eddy currents induced in this disk, uh, okay, by the another flux. So these two fluxes have same frequency. Both these fluxes will have same frequency, but they are displaced with time and space. Okay, these two fluxes will have same frequency, but they will have a displacement in time and space. Okay, as the interaction of the alternating fluxes is the base of this operation of this induction relay. Okay, these relays are not used for DC quantities. Okay, because in this relay, we are discussing about the interaction of the alternating fluxes. Okay, flux is alternative in nature, means it is AC quantity, not DC quantity. Okay, so this type of induction relays, they cannot be used for DC quantities, but they are widely used for protective relaying involving only AC quantities. Okay, they are widely used for the protective relays which involve only AC quantities. Okay. So now let us see the torque equation of the induction type relay. Okay. Now, so when alternating current is supplied to two electromagnets, okay, two fluxes will be produced. Okay, so one flux, let us assume flux phi 1 is produced in this electromagnet, and flux phi 2 is produced in this electromagnet. Okay, these two fluxes have same frequency, but they have a phase difference, let us assume, because they are displaced with time and space, so they have a phase displacement of around alpha. Okay, so phase displacement between phi 1 and phi 2, let us assume that they have a phase displacement of alpha. Okay, let's see. Alpha means I have to insert an symbol. Okay, so the phase displacement between phi 1 and phi 2 is alpha. And let us assume that phi 2 leads phi 1 by this phase angle. Okay, so among these two, the phase displacement is alpha, and let us assume phi 2 is leading phi 1 by an angle of alpha. Okay, so these two fluxes, phi 1 and phi 2, can be mathematically expressed as phi 1 is equal to phi 1m sin omega t, and phi 2 is equal to phi 2m sin omega t plus alpha, because phi 2 is leading phi 1. It's our assumption. Even phi 1 can lead phi 2. It doesn't matter. Just for understanding the concept, we have assumed that phi 2 is leading phi 1. Okay. Okay. So these two alternating fluxes, phi 1 and phi 2, let us assume this is our disk. Okay, so this disk I'm showing here. Okay, so this is our disk. So these two fluxes will cause the induced EMFs in this disk. Okay, they will cause induced EMF in this disk, means they will induce EMFs in this disk, and due to this induced EMF, eddy currents will be circulating in this disk. Okay, so those eddy currents are due to phi 1, I1 eddy current will be circulating in this disk, and due to phi 2, I2 eddy current will be circulating in this disk. Okay, so due to phi 2, I2 eddy current is circulating in this disk, and due to I1, phi 1, I1 circulating current is induced in this disk. Okay, so due to flux phi 1 and phi 2, which are having phase displacement of alpha, okay, EMFs are induced in this disk, and these EMFs will induce eddy currents, okay, I1 and I2, which are circulating in this disk. Okay, so these two circulating currents, I1 and I2, will react with each other to produce a force that acts on this disk. Okay, this I1 and I2 will react with each other, which will produce a force, okay, which will act on this disk. Okay, so these eddy currents will lag behind the respective fluxes by an angle of 90 degree. Okay, these two eddy currents, I1 and I2, will lag with their respective fluxes by an angle of 90 degree. Okay, so the induced voltages are proportional to the rate of change of flux, and hence eddy currents also. Okay, so we already know the induced voltage will be directly proportional to the rate of change of flux. E is proportional to d phi by dt, therefore current is also proportional to d phi by dt. Okay, so you can represent that in terms of equation. So since induced EMF is proportional to rate of change of flux, okay, similarly I is proportional to the induced EMF. Oh no, my voice is not audible. Okay, once again I will repeat. Okay. So current I1, the circulating current is proportional to the induced EMFs in the disk. Okay, so this circulating current is, and this induced EMF is proportional to rate of change of flux. Therefore, this circulating current will also proportional to the rate of change of flux. So phi 1 is what? Phi 1 is phi 1 m sin omega t. Okay, so if you differentiate, you will get phi 1 m cos omega t. So I1 is proportional to what? Phi 1 m cos omega t. And induced EMF is proportional, the current, circulating current is proportional to the induced EMF, and induced EMF is proportional to the rate of change of flux. Okay, so what is phi 2? Phi 2 m sin omega t plus alpha. So when you differentiate it with respect to time, you will get phi 2m cos omega t plus alpha. So I2 is proportional to phi 2m cos omega t plus alpha. I1 is proportional to phi 1m cos omega t plus alpha. Okay. So in this disk, their forces are produced due to the interaction of the I1 current and I2 current. Okay, in this disk, which is placed in between two electromagnets, okay, forces are produced due to the interaction of this flux phi 1 with circulating current I2. Okay, this phi 1 will interact with current I2 because it is circulating here, and it will because of the interaction of flux phi 1 with I2, force will be produced. Okay, one force is produced, and due to the interaction of flux phi 2 with the circulating current I1, okay, with the circulating current I1, some other force is produced. Let us give some notations for those forces. Due to the interaction of phi 1 with I2, a force F1 is produced, and due to the interaction of phi 2 with I1, force F2 is produced. So the direction of this force F1 and F2, if you want to determine, you can get it by Fleming's left hand rule. If you know Fleming's left hand rule, you can determine the direction of these forces F1 and F2. And these two forces F1 and F2 will be opposing each other. They will be opposite. They will be in opposite direction to each other. Hence, the net force acting on the disk. Okay, the resultant force that is acting on the disk. Okay, that is acting on the disk will be proportional to the difference of these two forces. Okay, the net force will be proportional to the difference of these two forces. You can see here, where is it? Okay, so F1 is proportional to phi 1 I2, F2 is proportional to phi 2 I1. Okay, therefore the net force F is the difference of F2 and F1. So it can be F1 minus F2 or F2 minus F1. Okay, it is just the difference of these two forces. So F2 is what? Phi 2 I1. So write down phi 2 I1, and F1 is what? Phi 1 I2. Okay. So F is proportional to phi 2 I1 minus phi 1 I2. Okay. So substituting the proportional expressions, that is phi, you know phi 1 and phi 2 expressions, that is phi 1 is phi 1 m sin omega t, and phi 2 is phi 2 m sin omega t plus alpha. What about this I1 and I2? Just now we have derived in the previous slide. If you see, I1 is phi 1 m cos omega t, I2 is phi 2 m cos omega t plus alpha. So you just substitute all those expressions of this okay, so if you substitute phi 2 I1 phi 1 I2 in this above expression, okay, so you will get like this. Okay, phi 2 is phi 2 m sin omega t plus alpha, I1 is phi 1 m cos omega t minus Okay, phi 1 is phi 1m sin omega t, I2 is phi 2m cos omega t plus alpha. Okay, so in this you can take phi 1m and phi 2m common. If you take phi 1m and phi 2m common, what will happen is it is in the form of sin A cos B sin B cos A. Okay, so sin A cos B minus sin B cos A. Okay, so you will get sin omega t plus alpha minus omega t. So omega t minus omega t, you will get f proportional to phi 1m phi 2m sin alpha. Okay, I hope you are able to follow. Okay, f is proportional to what? Phi 1m phi 2m sin alpha. So you can see from this expression what we can say is the resultant force f, okay, the net force, okay, is the net force that is acting on this disk will be proportional to sin alpha. Okay, so where alpha is what? It is the phase angle difference between phi 1 and phi 2. Okay, so phi 1m and phi 2m are the maximum values, isn't it? Phi 1m and phi 2m are the maximum values. You can replace this maximum values of phi 1m and phi 2m maximum values by RMS values. If I replace them by RMS values, my expression will be, okay, my expression here itself I am going to, I will simply remove this. Okay, so this is my RMS values of fluxes. Okay, so if I want to determine the net torque or force produced on the disk with the RMS values of the fluxes, okay, then F is proportional to what? Phi 1, phi 2 and sin alpha, where phi 1 and phi 2 are the RMS values of the fluxes. Okay, so it is very important to note that net force or the torque, okay, it can be force or you can even call, it can be, instead of force, you can say it as a torque, okay, because there will be angular movement there, therefore, better to use the word torque. Acting on the disk is same at every instant, okay, so at every instant, the net force will be same. The action of the induction relay under such force is free from vibrations. Okay, so the disk will, due to this net force or net torque, the disk will start to rotate in only one particular direction. Okay, and without any vibrations. Okay, so from this equation, okay, if we can say that if alpha is equal to 0, the net force is 0. Okay, so if alpha, this phase angle difference between these two fluxes is 0, then the net force is 0. That's what is understood from this expression, isn't it? Okay, so the disk will not rotate. Net force is 0 means disk will not rotate. Hence, there must exist a phase difference between two fluxes. If there is no phase difference between two fluxes, then the net force in the disk will be 0. When net force or net torque in the disk is 0, the disk will not rotate. Okay, so therefore the torque will be maximum when alpha is equal to 90. Okay, so when alpha is 90, the torque will be maximum. So the direction of the net force which decides the direction of rotation of the disk will depend on which flux is leading the other. Okay, whether phi 1 is leading phi 2 or phi 2 is leading phi 1. Depending on which flux is leading the other, direction of the rotation of the disk will change. Okay, so in practice there are various constructions, okay, which are used to produce phase displacement between the two fluxes. Okay, there are various construction to produce a phase displacement between the two fluxes so that the disk will rotate. Okay, okay, so you can see an image here. Both the fluxes phi 1 and phi 2 are having a phase displacement of alpha, and if you observe, I2 is lagging this phi 2 by an angle of 90 degree, and I1 is lagging phi 1 by an angle of 90 degree. Okay, so let us discuss types of induction relays. Based on the construction, there are various types of induction relays. Those are shaded pole type induction relay, watt hour meter type induction relay, induction cup type induction relay. Okay, there are three types here. Three types of induction relays are there based on the construction. Okay, based on the construction, three types of induction relays are there. They are shaded pole type induction relay, watt hour meter type induction relay, induction cup type induction relay. So let us discuss one by one. This is shaded pole type induction relay. Okay. So for more clarity, you can see this 3D image here. Okay. So this relay consists of an aluminum disc. This is the disc which is made up of aluminum material, which is free to rotate in the air gap of an electromagnet. Okay, so this is an electromagnet. This is an electromagnet in which in between this electromagnet, this disc is placed. This is the disc. Okay, so you can see this disc. Okay, a disc is placed between the electromagnet. Okay, so you can see here, these are the poles of this electromagnet. This is one pole, this is one pole. Okay, so each part of pole face of each pole is shaded with the help of copper band or ring, okay, known as shaded ring. Okay, so in this pole, you can see it has been divided into two sections. Okay, and one section or one part is provided with a copper band or a ring known as shading ring. Okay, so one part. Similarly, in the lower pole also, unshaded part and shaded part. Okay, so the total flux phi produced due to the alternating currents split into two fluxes, okay, displaced in time and space due to the shaded ring. Okay, so if you see here, this is our relay coil. Okay, this is a relay coil. When current is allowed to pass through this relay coil, what will happen? Flux will be induced in this core electromagnet. Okay, this flux will be split into two parts here, isn't it? The flux will be split into two fluxes. One flux is passing through a pole which is unshaded. So unshaded flux is phi u, and one flux is passing through a pole which is shaded, means it is provided with a copper band or a ring known as shaded shaded part. Okay, so the flux which is induced here, the flux which is allowed to flow through this part is known as shaded flux. Okay, so you can see in these two parts what is happening. Flux is dividing into two parts. Okay, the flux which is induced in this electromagnet is divided into two parts here. Okay, so due to the alternating flux, EMF gets induced in the shaded ring. Okay, when flux cuts this copper band, okay, so when flux cuts this copper band, EMF will be induced in this shaded ring or copper band. Okay, this induced EMF will cause a flux to exist in the shaded portion known as phi s actually. Okay, so because of the induced EMF in this shaded ring, phi s is induced. Okay, so whatever flux that is flowing through this shaded portion, that flux will cut this copper band. When flux cuts the conducting material, what will happen? EMF is induced. That EMF will induce a flux known as phi s. Okay, so let us assume phi s is the flux in the shaded portion, phi s, and phi u is the flux in the unshaded portion. And let us assume ES is the EMF induced in the disc due to phi s. Okay, and EU is the EMF induced in the disc due to phi u. Okay, let us assume IS is the induced current due to ES. Okay, due to ES, and IU is the induced current due to EU, and let us assume EU is lagging phi u. Okay, EU is lagging phi u by an angle of 90 degree. EU lags phi u, okay, by an angle of 90 degree, and ES will lag phi s by an angle of 90 degree. Okay, ES is lagging phi s by an angle of 90 degree, and IS lags ES by an angle of beta, and IU lags EU by an angle of beta. Okay, so the phase angle difference between this IS and ES is beta, EU and IU is beta. This angle is very, very small, so it is assumed to be negligible, and it is assumed that IS is in phase with ES and IU is in phase with EU. Okay, since this beta angle is very small, you can neglect it, and you can assume that IS is in phase with EU and IU is in phase with EU. Okay, so this is the phasor diagram of the component of the working components here. Okay, for this relay, and the resultant flux in the disk phi due to this unshaded flux and shaded flux is phi. Okay, and this let us assume that this phi u and phi s are having a phase angle difference of alpha. So you already know that just now we have discussed about the induction relay. In that, what we have discussed is that there should be phase angle difference between the two fluxes that are induced in the disk. Otherwise, there will not be any force or torque induced in the disk. The disk will not rotate. Okay, so phi s is lagging phi u by an angle of alpha. Okay, so this phi s is lagging phi u by an angle of alpha. Therefore, the net torque, okay, the net torque that is produced. Wait, I will just copy it from the previous slide, and I am. Okay, so the net torque that is produced in the disk is phi s into phi u sine alpha. Okay, the net torque that is produced in the disk is phi s and phi u are having phase displacement of alpha. So the net torque that is produced in this disk, okay, so that is proportional to phi s phi u sine alpha. Okay, so assuming phi s and phi u to be proportional to the current I. Okay, assuming phi s and phi u to be proportional to current I. So phi s and phi means proportional to current I means as the current supply current in the relay coil, okay, the actuating quantity, that is I here, as it varies, as current varies, the flux induced in this electromagnet will also vary. When the flux induced in this electromagnet will vary, okay, the flux in these two unshaded portion and shaded portion will also vary. So phi u and phi s are depending on I, they are proportional to I. So you can replace phi s by I and phi u by I. Okay, so you will get I square sine alpha. So torque is proportional to the actuating quantity I. Okay, the current which is
Ma'am, your voice is not audible.
So did you miss this? Okay, 1 minute. Yeah. Okay. So when the actuating current is varied, okay, the current flowing through the relay coil is varied, the flux in the electromagnet is flux in the electromagnet will vary. Okay, when phi is varied, the amount of flux flowing through this unshaded portion will also vary. When the flux in this shaded portion varies, the induced EMF in this shaded ring will also vary, and hence the flux that is produced due to the EMF induced in this shaded portion or shaded ring or copper band will also vary. So phi u unshaded portion flux and shaded portion flux is proportional to the current that is flowing in this relay coil. Okay, since the phi u and phi s are proportional to the current that is flowing in the relay coil, so phi s is proportional to I, phi u is proportional to I. So I into I square. So torque is proportional to I square sine alpha. Okay, so for a given particular design, sine alpha will be constant. So I can say torque is proportional to I square. Okay, so torque in this shaded pole type induction relay is directly proportional to the torque that is induced in this disc. Okay, the torque that is induced in this disc will be directly proportional to the square of the current that is flowing through this relay coil. Okay, so when torque is induced in this disc, what will happen is, when torque is induced in this disc, what will happen is, you can see here to this there is a spring coil here. Okay, this is the shaft that is mounted on this disc. To this shaft there is a moving contact. This is the fixed contact. Okay, so this is the fixed contact of the trip circuit. Okay, so there should be two contacts, but in order to understand the concept, this diagram is more easy, means it is much useful to us. That's why I'm showing you this image. So when the disc rotates, what will happen? This moving contact will come in contact with the fixed contact, and trip circuit is closed. When the trip circuit is closed, what will happen? Trip coil is energized. When the trip coil is energized, circuit breaker is open. Okay, so the torque induced is proportional to I square. So when as the current in this means, if under normal operating condition, okay, of course the induced torque in the disc will not be sufficient enough to allow this moving contact to come in contact with the fixed contact. Whenever fault occurs, okay, since torque produced is proportional to square of the current, okay, the disc will rotate, this disc will rotate, and this moving contact will come in contact with the fixed contact. Okay, so this is the operation of this shaded pole type induction relay. Next is watt-hour meter type induction relay. So the construction of this watt-hour meter type induction relay is similar to the watt-hour meter, which is very popularly used everywhere. Okay, you know what is watt-hour meter. Okay, so this relay actually has two winding structure. Okay, you can see here this winding is known as primary winding. This winding is known as secondary winding. Okay, primary winding is nothing but the relay coil. Okay, relay coil itself is the primary winding. This is the secondary winding. It is written here. This is the secondary winding. Okay, so this watt-hour meter type induction relay will be consisting of two magnets. One is E-shaped magnet, other one is U-shaped magnet. Okay, E-shaped magnet as well as U-shaped magnet. Okay, so and in between E-shaped magnet and U-shaped magnet, there will be a disc which is free to rotate. Okay, this disc, there will be a disc which is free to rotate, and this E-shaped magnet will carry two windings. One is primary winding, another one is secondary winding. Whereas this U-shaped magnet will carry only one winding, that is secondary winding. Okay, so the U-shaped magnet carry secondary winding. E-shaped magnet will carry primary winding as well as secondary winding. Okay, so this primary winding is nothing but the relay coil. So when current of I1 amperes is allowed to flow through this E-shaped magnet, what will happen when current flows through this coil? Flux is induced. Phi1 flux is induced in this E-shaped magnet. Okay, so Phi1 is not written. Phi2, you can see Phi2 here. It should be Phi1. Phi1 flux will be induced in this upper magnet. In some other image, you can see. See, this is Phi1. Phi1 flux is induced in this upper magnet. Okay. So when this flux cuts this secondary winding coil, what will happen? EMF will be induced in the secondary coil. And since if you see the secondary coil is having a closed path, current of I2 amperes will flow through the secondary coil. Okay. So when fault current flows through this relay coil, that is I1 current. Okay. Because of that current, what will happen? Flux will be induced in this E-shaped upper magnet, and this flux will cut the secondary coil, okay, in this same magnet. And what will happen? EMF will be induced in this secondary coil, and because of that induced EMF, then since this secondary coil is having a closed path, current of I2 amperes will flow through this secondary coil. Okay. So now when current is flowing through this lower magnet, now what will happen? Flux of Phi2 Webers will be induced in this lower magnet. So the flux in the upper magnet is Phi1, flux in the lower magnet is Phi2. Okay. And let us assume this Phi2 is lagging Phi1 by an angle of alpha. There is a phase angle difference between these two fluxes. Okay. The phase angle difference between these two fluxes is alpha. So due to the interaction of these two fluxes, torque is exerted in this disc and this disc will rotate. Okay, so due to the interaction of Phi1 and Phi2, torque is induced. How torque is induced, we have already discussed. Okay, and this disc will rotate. Okay, so the torque induced will be proportional to what? Phi1 into Phi2 into sine alpha. Okay, so as let us assume Phi1 is Phi1 flux will enter into this disc. Okay, from upper magnet, and Phi2 flux will enter into this from lower magnet, and torque tau is induced in the disc, which is proportional to Phi1 Phi2 sine alpha. Okay, and when the torque is induced, what will happen is, this is, you can see here, this black rod like thing. This is the moving contact, this is the fixed contact. These two are the fixed contact, this is the moving contact. So when the disc rotates, what will happen? Moving contact will come in contact with the fixed contact. When moving contact comes in contact with the fixed contact, trip circuit is closed. When trip circuit is closed, trip coil is energized and circuit breaker is open. Okay, so to this primary winding, which is the relay coil, we can even provide tapping. Okay, we can even tap this primary winding. I have one more image. So this primary winding can be tapped. Okay, we can provide tapping. So with the help of suitable number of primary turns, we can select the number of turns in the primary. Okay, in order to vary the current setting of this relay. Okay, at what current this relay should operate, we can decide by providing tapping. Okay, so important feature of this watt-hour meter type induction relay is that its operation can be controlled by opening or closing the secondary winding. Okay, if you want to control its operation, simply disconnect the secondary winding. So secondary winding is disconnected. Okay, so it won't form a closed path. Okay, it won't form a closed path even though current is flowing through the relay. Okay, relay coil. Even though flux Phi1 is induced in the upper electromagnet, Phi2 will not be induced in the lower electromagnet. Because why? Because there is no closed path for this secondary coil. Okay. So whenever secondary is open, no current will flow and Phi2 is not induced. Okay, so whenever you want to make this watt-hour meter type relay inoperative, then you can simply open the secondary winding. That's all. This is the operation of a watt-hour meter type relay, induction relay. Next is induction cup type relay. Okay, I know. So you have another class. Okay, I'll continue this topic in the next class.